So here's a second example of a separable differential equation we can solve. I know that dy dx equals negative 2x over y. And I know, I'll write it up here, f of 1 equals negative 1. So my job is to find the y, the function y, that makes this statement, well, that makes the two of these statements true. So my technique for doing that, in cases where I can, and on the AP test, it will be a separable differential equation. If they ask you, they won't try to trick you. To think about multiplying both sides of this equation by dx. My new equation, dy equals negative 2x dx, wow, dx over y. My goal is to get everything that has to do with x on the right side and everything that has to do with y on the left side. And make sure that as I do that, my dx and my dy end up in numerators. They can't be in denominators because I'm going to be using integrals, and we've never had an integral where the dx was in a denominator. This doesn't fit what we know about what definite integral, what any kind of integral represents, which is adding up a bunch of two things multiplied together. So my next job, what could I do? This is the thought process I have to have. Because right now I see y on my right-hand side of the equation, and I want to make it so I have no y's on the right. So over here, the y is in a denominator, so we're getting divided by y. So I have to ask myself what undoes dividing by y, and that's going to be to multiply by y. So I'm going to multiply both sides of this equation by y. Here's my new equation, y dy equals negative 2x dx. I've now separated the x's and the y's into separate sides of the equation. That's what makes this a separable differential equation. So now that I have this, I'm going to use that same idea we've been using for a long time since algebra, that it's legal to do something to one side of an equation as long as you do it to the other. And the thing I'm going to do, I'm going to integrate. So I'm going to write this up here, y dy equals negative 2x dx. And I'm going to integrate both sides. So what does that mean? That means I'm going to essentially make both sides the integrand in integrals. And now I'm going to think of this as two separate problems. In like 6.1 and 6.2, we learned to look at indefinite integrals and write antiderivatives. So the antiderivative of y with respect to y is y squared over 2. That's me using the reverse power rule on y to the first power. And on the other side, I'm going to have a negative 2 multiplier. The antiderivative of x is x squared over 2 plus a constant. Now remember, really I should have had a constant on both sides when I integrated, but then the very next thing I'm going to do is move one constant to the other side and make a brand new constant. So there's a little shortcut everybody accepts, which is when I integrate both sides in a differential equation, I'm only going to put my plus c on one side. Now if you could simplify that negative 2 and that 2 in your mind as you did this, that's fine. You don't have to show all these steps. I'm going to show all the steps, especially at the beginning. It can be tricky to keep track of where you are. So I'm going to simplify this. So I'm going to say like 1/2 y squared equals negative x squared plus a constant. And at this point, this is what I do. I find c first, because my next job is going to be to isolate the y. The two jobs I have are to find c and isolate y. And sometimes isolating for y can go a little faster if I don't have an extra variable, this plus c that I'm sort of carrying around. So I'm going to have some kind of break. Sometimes I move off to the side. Sometimes I put these little lines here just to say, okay, I'm going to do something different now. And I'm going to use this ordered pair, f of 1 equals negative 1, to say that 1/2 This is the y. Negative 1 squared equals the opposite of 1 squared plus a constant. So that's me taking the same function I've been working with. Maybe it doesn't look like a function yet because I haven't really isolated y. But this equation, I know this is how x and y are related. And I'm going to use the ordered pair that I've been given, it's called the initial value, to figure out what c is. So negative 1 squared is positive 1. This is going to be 1/2 on this side equals negative 1 plus c. I'm going to add 1 to both sides. That was me adding 1 plus, and I get that 3/2 equals c. Just to sort of keep track, if this were the AP test, this might show up as a free response question. Separating the variables, so getting to this stage, is worth 1 point. Finding your antiderivatives correctly, which I did here, is worth either 1 point each, or sometimes 1 point for getting them both right. Remembering to use a plus c is, just remembering to have a plus c is worth 1 point. Figuring out what c is by using that initial value is worth 1 point. It's going to be worth one last point if I can isolate y. So I'm going to write down what I know so far, which is that 1/2 y squared equals negative x squared plus c, but I just figured out that c is 3/2. So I'm going to regroup back here. I've gone back to the relation I had between x and y, but now I know what c is. My last step is going to be to do whatever algebra I need to do to isolate y. So let's see. I might multiply both sides of this equation by 2 to get y squared equals negative 2x squared plus 3. And now if I ask myself what's happening to y is getting squared. To undo squaring, I take the square root of both sides. Oops. But when I do that, I need to use a plus or minus sign. So here's my new equation. Y is equal to the positive or negative square root of negative 2x squared plus 3. And that's pretty good because my goal was to isolate y, but notice what happened. When I isolated y, that process of taking a square root, I needed to use the plus or minus sign, and what I have is not a function of y. If a function takes one x value and assigns it to exactly one y value, but here, with that plus or minus sign, I'm giving 2 possible y values. So it's my job at this point to stop and figure out, should I keep the plus sign, the positive sign, or should I keep the negative sign? So I go back to that same ordered pair I had. Remember, this is the ordered pair, x is 1, y is negative 1. And I asked myself, if I'm going to plug in a positive 1 for x, and I need a negative 1 to come out, should I keep the positive sign or the negative sign? We probably noticed that we should keep the negative sign. This is going to be the opposite of the square root of negative 2x squared plus 3. This is a great answer. This answer probably gets full credit. They have sometimes on the AP test also given a point for a correct domain statement in this case. So I noticed that the answer I've given is not defined for all real numbers. Square roots are only defined when the inside is a positive or non-negative at least. So hold on. So I'm going to come up here to the side and I'm going to say that the domain for my function, my answer is supposed to be a function, the domain for that function is going to be all the x's so that the inside of the radical, which is the opposite of 2x squared plus 3, has to be greater than 0. I'm going to isolate the x here, so I'm going to subtract 3. I get negative 2x squared is greater than negative 3. I'm going to divide both sides by negative 2, which means I'm going to have to flip the inequality sign around. And for x squared to be less than 3/2, that means negative 3 over 2 is between, x is between negative 3 over 2 and positive 3 over 2. So this answer is my function. It's the solution of the differential equation. This is the domain statement for my solution.